Hi everyone. In this video, I'm going to talk about the basic setup of a VLC system. We'll go over the basic key components and parameters that enable communication using LED lights. Also, I apologize for the delay in uploading a new video, dealing with multiple things. Anyways, let's get back to the topic. Similar to conventional RF communication, VLC systems use LED lights as transmitters. To optimize them for practical use cases, extensive research has been conducted over the past 10 years, particularly focusing on different types of LEDs and their effectiveness in data transmission. For example, while white LEDs are commonly used, RGB LEDs have also been studied to assess their suitability for real-world applications. A few papers on different types of LEDs proposed in the literature for your perusal. Okay. Now let us consider an LED light installed on the ceiling of a room, and connected to an electronically controlled circuitry designed to enable data transmission via visible light. While at the receiver end, the photodiode, which by definition converts incident light energy at the photodiode into useful electrical current, is considered. And photodiodes really are the go-to choice for a basic visible light communication setup, and it's easy to see why. Actually, the area of photodiode which can comfortably convert the optical light energy into electrical current is in centimeters, so we can pop it into any handheld smart device without extensively modifying the internal or external design of the device. Also, photodiodes are sensitive to light and provide reliable performance in noisy environments, therefore, suitable in different applications and use cases. But, the best of all is the optical to electrical conversion ratio, which we technically referred to as responsivity. If I briefly tell you about responsivity of the receiver, it is basically defines how much electrical current is induced per unit of the incident optical power, and we measure responsivity in amperes per watt. So, in simple terms, higher responsivity means higher conversion ratio. One more important aspect is that the sensitivity of the photodiode greatly depends on the material it is made from. Like as we assumed a silicon-based photodiode, this type of material is easily adaptable and sensitive to both LED-enabled visible light region as well as the upper frequency spectrum in the infrared region. It means higher frequency resources in the visible light wavelength region can be effectively exploited if there's no obstruction or interference in the light propagation channel between the transmitter and receiver. One of the papers also discussed about the responsivity of the receiver and validated that the silicon-based photodiode responsivities are around 0.2 ampere per watt at around 400 nanometers wavelength, while 0.6 ampere per watt at the peak. I have also added that paper title, so you can give it a read at your convenience. Though camera-based receiver is also considered by the researchers of the well-known companies, but it is beyond our today's topic and I will make a separate video on the light receiving technologies. I am also not going in deep to discuss about the physics behind optical to electrical conversion, like how photons react and excites the electrons and how these carriers flow through the external circuit, etc., but I will surely make a separate video on this as well. Additionally, optical filters placed in front of the photodetectors pass only the LED's emission band, for example, a narrow range around 525 to 630 nanometers, and block all other wavelengths, thereby improving the signal-to-noise ratio. Alongside optical filters, optical concentrators are used to gather and focus incoming light signals onto the photodiode's active area, making up for the detector's narrow field of view, FOV. The FOV is the widest angle over which the receiver can collect light. Although it can be as large as 90 degrees, the FOV is often optimized to meet specific system requirements. Tuning the FOV helps the receiver concentrate on the intended signal path and reject unwanted background light. Now, after setting up the transmitter and receiver, and if we want to calculate the visible light channel between an LED transmitting data packet in a clear, line-of-sight scenario with no blockage from surrounding environment, the channel attenuation of LED-enabled visible light signal is formulated as. The given analytical expression of the visible light channel is derived by using analytical geometry but can also be evaluated by vectorization. Also, you can see the angles between the LED transmitter and receiver in the figure. This is how we calculate angles between the transmitting node and receiving node. There are also a lot of technicalities involved in establishing a connection between the transmitter and receiver in the first place, and how both devices stay connected, so a lot of things work at the back end. Anyways, let's get back to the topic. The parameters shown in the expression can be defined as, M is the Lambertian emission order of the transmitting LED, S is the miniature area of the optical energy receiving photodiode, and we have already discussed about the size of the photodiode, which is normally in centimeters, and D is the Euclidean distance between the transmitting LED and VLC receiver. As I updated that, we have used geometry wherein we calculate angles, so the first angle in the equation, that is cosine phi, is the angle of irradiance. Irradiance means if the LED is looking downward, then we can say that LED radiation pattern or irradiance angle is towards the floor. Similarly, the cosine SI is the incidence angle of the propagating light radiation at the receiver, and TS and GS are the optical filter and concentrator gains. Nonetheless, visible light channels are highly susceptible to frequent propagation path losses and can deteriorate the communication performance. Here, we are assuming a very ideal condition just for understanding all important VLC enabling parameters, but in practical scenarios, light signals significantly deteriorate due to different types of environmental challenges, such as walls, furniture, and even a human body can weaken the signal up to 40 dB. Now, let's say if we know the location of the LED and the receiver and total area of the geographic location, like office room, classroom, school lab, etc., and if we know all essential parameters discussed earlier, we can easily calculate the channel gain or channel attenuation factor of the VLC wireless network. Though we normally use Cartesian coordinate 3D system, but different other coordinate systems can also be exploited, it is totally based on our requirements. So, this is what a basic VLC communication setup looks like, though I know a few concepts need more clarity. For example, light exhibits wave-particle duality, so why and which behavior do we commonly consider in VLC networks? Fundamentally, it is a physics concept, but let's revisit those basic ideas in the context of VLC. Alright. Thank you for watching. Bye for now.